Okay, so here we're going to find the volume of a solid. The solid is going to lie above the xy plane, below the plane z equals 1, outside the paraboloid, and inside a cylinder. So the first thing we probably should do here is go ahead and sketch this thing out a little bit. So here's some axes, and I generally like to do these by sketching out a cross section. So this is going to represent the xy plane and the vertical axis z. So let's see what we've got. We've got a cylinder of radius 1. So let's sketch that onto our graph. Again, we're looking at a cross section, so the cylinder is going to come up from the xy plane and be a distance of 1. So we'll take that as our cylinder. And we know that it's capped on top by z equals 1. That being that the solid has to lie below z equals 1, meaning that this is now the top. So here's our line, z equals 1. And this one's a little bit confusing the way that it's worded, in the sense that they've told us that it's going to be outside the paraboloid here. Now the paraboloid is actually going to sit inside the cylinder and do something kind of like this. So when we say we're outside the paraboloid but inside the cylinder, what we're really saying is that we're bounded vertically between the paraboloid and the plane z equals 1. So this is where our region is going to be. This solid E is going to lie in here. Based on the way that the problem is worded, we would assume that we're going all the way around the z-axis with our shape. So when we look at this from the top down, what we would just see is a circle of radius 1. We have a cylinder, so that's going to give us a good idea that we should probably do this in cylindrical coordinates. And of course our region in the xy plane here is also circular, another good indication that using cylindrical coordinates is a better way to go. Now I've also plotted this out on CalcPlot 3D here, so we can get a feeling for what this shape looks like as well. I'd see it a little more clearly even than we had there. So it's pretty obvious. You can see the paraboloid inside there, that hole that we've kind of drilled out of the bottom of this cylinder. And if we look down from the top straight down, we can see that circle of radius 1 that represents our region in the xy plane. So that's our solid. Let's head back to the problem now. Okay, so we're going to need some bounds here for z, r, and theta. The z limits are going to come from bounding above by z equals 1 and bounding below by our paraboloid. So let's lay that in, bounded above by 1 and below by the paraboloid. We do need to convert this to polar coordinates, so that makes it 1 minus r squared less than or equal to z less than or equal to 1. So to find our bounds for r and theta, we'll look over here at our projection into the xy plane. The radius is going to go between 0 and 1. So 0 less than or equal to r less than or equal to 1. And theta is going to go all the way around from 0 to 2 pi. So we have 0 less than or equal to theta less than or equal to 2 pi. So now it's just a matter of throwing it onto a triple integral. And we're there. So let's set that up. We have our triple integral. We're finding volume, so we're just integrating 1 dv. But v for cylindrical coordinates, you'll remember, is r dz dr d theta. Our z bounds go from 1 minus r squared to 1. R is going to go from 0 to 1, and theta is going to go from 0 to 2 pi. So there's your setup. Of course, 1 times r is just r, so we might as well do that.